turn on the computer then.
Okay.
All right. Hello and welcome to the Calc 2 review session. This is because we're just starting the review. You're already here. You already know the drill. We are going over problem 1 of
From 9.1, I think.
yeah, problem 1 for homework 9.1 first.
Did the other person come back? Or no, it's
No,
the
that's
person.
the
Okay.
person. Oh, and they left. Oops. You really hope it's starting. No.
I'll be glad I hope.
I believe it.
Okay. Probably have to do something wrong, but
Okay, we're watching. Let me just pin your. Helps if you just pin the video so you can see it. All right.
Was there another person? Or was
There is another person, but since we're recording, they can always go back.
Okay. All right. So this problem, we start with a differential equation, and then it gives us a couple options for the solution, and it's a multiple choice. So I'll just write down a few of the solutions that they give you as possibilities, and then we got to find the one that actually fits for the differential equation. So, okay. All right, so these are the three possibilities that will work for a solution for this differential equation. So what we do to solve this and figure out which of these three it is, we go ahead and we take the derivative of each of these equations and then plug them in to this top differential equation here. And then we got to see if both sides are equal. And if they're not, then that's not a solution. And if they are equal, then it is a possible solution. So if I just start with the first one, I'll just call them A, B, and C. So if I take the derivative of A, I get 6 minus 8x2. So then I take this derivative and I plug it into this top equation. So if I do that, I have x times y prime, which was 6 minus 8x to the negative 2 plus y. And our original y was 6x plus 8x to the negative 1. We plug that in just like that. 6x plus 8 times x to the negative 1. That's equal to 6x. So then we go through and we simplify it, and we're going to see if it is equal to 6x. So we can distribute this 6 through. So we'll have 6x times plus 6 plus 8x 6x. As we can see here, the negative 8x to negative 1 and the positive 8x to negative 1 are going to cancel out, and you'll get 12x, which is not equal to 6x. So we know that right now, solution, the first equation A is not a solution. So I'll put an x next to it. So we'll do the same process for our second equation, B. So we'll take the derivative of y. So we're going to get negative 8x to negative 2 minus 3. And then we take this derivative here, we plug it into the differential equation. So we have x times y prime, which we just found. And then we add y, and our original y equation was this one. So we add that. And we set that equal to 6x. And then again, we're going to distribute our x in this first term. So we're going to have negative 8x to negative 1 minus 3x plus 8x to negative 1 minus 3x equals positive 6. So the negative 8x to negative 1 will cancel out. And then we're gonna be left with negative 3x and negative 3x. That's gonna give us negative 6x, which is not equal to 6x. So we're gonna also conclude that this equation, B, is not a solution. So we're gonna check the last one and hopefully that is a solution to the equation. So we're gonna take the derivative of the equation C. So y prime is gonna be equal to 3 minus a negative 8x to negative 2. I'm just gonna simplify that, and that's 3 plus 8 times x to the negative 2. And then we're gonna take this equation and we're gonna substitute in for our y prime in our differential equation. So if we do that, we have x times 3 plus 8 times x to the negative 2 plus y, and y is just our initial equation here. So plus 3x minus 8x to the negative 1, and we're gonna see if that's equal to 6x. All right, so again, just like the other ones, we're gonna distribute this x among these two terms. So we're gonna have 3x plus 8x to the negative 1 plus 3x minus 8x to the negative 1. And we're gonna see if that's equal to 6x. And if we combine like terms, those are gonna cancel out, the negative 8 and the positive 8, and the 3x and the 3x are gonna add together to become 6x, and 6x is equal to 6x, so that checks. Then we know that this equation is a solution to the differential equation. And so that's how you go about choosing from a list of possible solutions. Are there any questions on that example?
If there are no questions about this example, feel free to either say out loud or in the chat if you want to go over a specific problem or topic. We are happy to oblige.
Mm-hmm.
And for those that joined halfway through, this was problem 1 on homework 9.1. Right?
Yep, 9.1. Mm-hmm. So if there's any other differential equations type of homework that you guys want to look at while we're on this homework section, feel free to put that in the chat or mute yourself.
I'll just give another 10 minutes for questions.
Mm-hmm.
Number 8.
Okay. And this is from section 9.1?
Yeah.
Okay. All right, so this is 9.1, number 8. All right, so I'm just gonna read the problem. All right, so we are given a differential equation, which is, let's write it real quick. Okay. Yeah. Okay. So just setting that equation.
Yeah.
Okay.
Finding
Okay, so for the first part of this problem, it asks us to find the constant solutions of the equation. And to do that, we're going to set our derivative equal to 0. So if we set our derivative equal to 0, we're going to have just the same terms on the right side, but we're going to have the 0 on the left side. The next thing I'm going to do is I'm going to factor this. And as you can see, there's a y squared in every term at least. So I'm going to pull out a y squared. And if I do that, I'm going to get y squared here minus 14y there, and then plus 48. And you can check that by distributing through that y squared. And then you will get this equation that we started with. So the next thing we want to do is we want to find all the places in this equation that we can get 0. So I like to break this into like 2 types of terms here. I have a y squared I'm first look at, and then I'll look at the rest later. So if we just ignore the right-hand part, what does y have to be so that this is equal to 0? Y has to be equal to 0. And then if this is 0, you multiply it by whatever is over here, the whole thing's going to be 0. And then I'm going to look at just the right-hand side of this then. And to go through with that, I'm going to factor this side. So I'm just going to factor this. So I need to find two terms that multiply to 48 and add to negative 14. So looks like that would be -6 and -8. -8 times -6 gives us a positive 48. And if you add those two, you get -14. So that's a quick way you can factor that as long as the coefficient on the y squared is a 1. So if we look at now these two terms, we're going to look at this middle one first. What do we have to make y be so that this whole thing is equal to 0? We'll make y be equal to 6. So if it's 6 minus 6, we get 0. 0 multiplied by any of this will give us 0. So y could also be 6 to make this go to 0. And then likewise, y could also be 8. To make that be equal to 0. So those are the constant solutions of the equation. So y equals 0, 6, or 8. That's for the first part of the question. So again, to find that, you just set the derivative equal to 0, and those would be like your critical values that you find.
Also, one side note, I finally realized why you set the derivative equal to 0. Since your y solutions are constants, if you take the derivative of a constant, you get 0.
That's a good way to think about it as well. All right, so then we have the next part. It asks us for what values of y is y increasing. So they want us to answer this in interval notation. So what I like to do for this is make a number line. And I like to put my critical values right in the number line. So I'll have 0, 6, and 8. And then I'm going to just plug in these. I'm going to see in these intervals. So like negative infinity to 0, 0 to 6, 6 to 8, and 8 to positive infinity. If it's going to be positive, negative, and that would tell us if it's increasing or decreasing, if it's a positive or negative value in between these intervals, sorry. So first I'll just choose a very much negative value for our y. Am I doing this right? Yeah, okay. So if I choose a really negative number, I'm gonna have so that's gonna be 4. What's that? That's gonna give me positive, right? I think.
Yes, yeah.
Yep, and then
Show you a fun aid if you want me to.
what's that?
You use what you got right here.
Uh-huh.
If you just plug in a negative number like -1, you see this is always positive. That's going to be negative.
I see what you're
That's going to
saying.
be negative.
Okay, that makes sense.
That's what I do all the time. So
That
I
makes it
actually-
way faster.
Yeah. So here, do you want me to write this down real quick?
For sure. He's got a good method here that's gonna help.
Yeah. I've had plenty of years working on this. So
Yeah.
here's a nice visual aid for when you're doing these number lines. So what you want to do is you want to go back to where you factorized everything. So you'll see we have y squared, y minus 6, y minus 8. So I like to separate it into 3 parentheses. And then, so since we're a number less than 0, I like to choose a simple one, -1. So you plug -1 in for y everywhere. So for y squared, -1 becomes positive because you have a negative times a negative. So in this leftmost parenthesis, I just write a positive. Here we have -1 minus 6. It's going to be again negative. Here again, it's going to be negative because it's -1 minus something. So now since we have an even number of negatives, we know that it's going to be positive overall. I like to use this trick everywhere because it's a really shorthand way that doesn't require me to do too many calculations. So here between 0 and 6, we plug in 1. This will be positive. This will be negative, and this will be negative. So again, we just go like that. So see there's no change in, so we'll see that here it's positive, 0, and then back to being positive. And then when we get to 6, so let's plug in a number between 6 and 8, 7. So 7 squared is going to be positive. This also prevents you from having to use a calculator too much, which is why I like it. So now 7 minus 6 is actually positive now, but 7 minus 8 is still negative. So we get a negative sign here. And then if we plug in any number greater than 8, positive, positive, positive.
That's good.
Yeah, so this is a really helpful tip. I teach it to everybody that I go over Calc 2 with because I find it helpful as a visual aid. And also it typically makes it go by faster since you don't have to plug in numbers all the time.
Yeah, that's a really good idea to use our most factored form here to go through that instead of trying to crunch numbers up here. Yeah, so that's good. So anywhere we see a positive sign, that's where our function is going to be increasing. And we see the negative sign, that's where it's going to be decreasing. So for part B, it's asking for the values of y when y is increasing. So if we want to answer this with interval notation, just to get a little practice, remember we use a parenthesis like this. If it's like infinity, right, we can't contain infinity, so it's not going to be a square bracket. So we're going to go from negative infinity up into 0, and then 0 to 6 was also increasing, and then 8 to infinity was positive, so that's also increasing there. And then for part C, it was asking the interval which it was decreasing on, and that's where you have a negative sign, that's a decreasing interval, so that would just be the interval from 6 to 8. And that's question 8 from section 9.1.
You can clearly tell I like that trick.
That is so cool. Wow, I wish I knew that when I was taking calc.
I forgot if my teacher even taught me that or if I just came up with it on my
Like, it makes so much sense now, you know, when you're looking at it, it's like,
Most people would never think of it though, because normally when you're doing math, you need hard numbers. So
for sure.
it's a nice shorthand though. And it means that some of your work isn't wasted.
Yeah, true.
If you don't have any questions about this problem, you can always ask a question about another problem or topic. If you're really struggling with the topic, we can review it for you. I forgot how I came up with this.
Could we do one of the problems from 9.4, the population growth models?
Okay.
Okay.
Population.
Was there a
growth
specific
models.
one from 9.4?
Population growth models. So from
Okay.
any of the questions,
Okay.
let's see. I can pick a good one. That might be a good one.
Do you want to go through it?
Yeah.
Okay.
Go over it. All right. Maybe calculations, but sure. All right. All right. We are going to work on number 2 in homework 9.4. So let's do that. All right. So let me just share it on the screen. So 9.4, number 2. So we have a differential equation, dp over dt is equal to 0.09 p minus 0.0009 p squared. All right. And t is measured in weeks. So what is the carrying capacity? So carrying capacity, we need to figure out basically where the growth is zero, because carrying capacity, we are obviously never going to like exceed normally, or if we do exceed, it's going to go back down to zero. So we need to find effectively a critical point. So where dp dt is equal to zero. So if we were to solve this, so we have equals 0.09 p minus 0.0009 p squared. So obviously we have the solution 0, but we're not going to assume the boring solution where the carrying capacity is 0, because clearly if that was the case, we wouldn't all be alive right now. So what we do is just solve. So I'm just gonna add, add over this to the other side, because I find that easier. So we have 0.0009 p squared is equal to 0.09 p. So now we have a p on both sides. We can cancel by dividing by p. So now we have 0.0009 p is equal to 0.09. That's a lot of zeros. So now we just divide by this. So we get p is equal to 0.09 divided by 0.0009. So since we have a factor of 9 in both, we can cancel that, just write it as 1. And now we have, so 0.01 divided by 0.0001, or I can rewrite this as 10 to the negative second, that's counting decimals, over 10 to the negative fourth. So since it's division, we subtract powers, so -2 minus -4, we get 10 squared, which is equal to 100. So our carrying capacity is equal to 100. And that is for part A alone. So carrying capacity. All right. So now part B, we need to find the value of K. So this is where we have to actually go to solving the differential equation, right? Oh, wait. Oh, there might be a formula for us to use here. I think there's something like dp is equal to k, and then, well, actually, I think we're at kp, and then it's the carrying capacity. I'm just going to write c minus p. I think that's it. Can anybody confirm if you have a formula like that? This might be different, like it might be a p naught or something. Either way, it should be a constant. Kind of pulling on thin air because it's been a while since I've had to do Calc 2. I want to say that's right.
I don't remember.
Because if that's the case.
It says dp equals, or dp over dt equals kp times the quantity of 1 minus p over L.
Oh, 1 minus p over L. Okay, yeah, that works too. So let me just cross that. Kp, and then 1 minus p over L. Is L labeled as your carrying capacity?
Yeah.
Okay, yeah, that makes sense. So what we do then is, all right. Yeah, it's important that I have the right formula because otherwise our K will be slightly different. Because effectively what I would have had here is, so I distributed a 1 over L out of here. I have L up here instead, and then it would actually be K over L. But, so, all right. So using that, we just plug in everything. So we get dp dt equals, so K, and then we can actually write, so K times 1 times P, just distributing everything in. Then minus K over L P squared, oops, P squared. And then that has to be equal to 0.09 P minus 0.0009 P squared. What you'll end up finding is, so if we need this to be true, then this has to equal this. So these have to be equal to each other. Well, this one doesn't really matter. We have a P, so K has to equal 0.09. So that's just a quick trick to doing it instead of having to work out the whole problem. So that's actually still part of A too. Part B, we have a direction field for the equation. So we need to ask, where are the slopes close to 0? So we kind of already went over where the slopes are 0 because I used it to solve for the carrying capacity, didn't I? So at the beginning, I also mentioned, so P can equal 100, but it can also just equal 0. And so that's just because, well, this is true. We have a P term in here, so you can distribute that out. We get P 0.09 minus 0.0009 P. So if that has to equal 0, either P can equal 0 or P can equal 100 like we set up here. So for part B, we have P equal to 0, 100. And I believe, oh, that is not all they're asking. Okay, so I'm gonna have to flip this over for a bit. Any questions about this part so far? Yes, no? I'm gonna assume that's a no. Gonna move on to the next. So now we're trying to find, so where is slope the largest? So this, you can make it an analytical thing, or you can make this a very intuitive thing. So for these growth models, what ends up happening is you'll plateau at your carrying capacity. You'll have a slope of 0 also when the population is 0. And then in between there, so this is what most of them look like. You have this. And you'll notice that right about here, which is halfway between, so we can say that's our L. This is about L over 2 every time where the slope is the largest. So where's the population the largest? When P equals 1/2 of carrying capacity, which is 50. And if you're looking at the direction field, it will fairly, if you're like that, you'll notice that at 50, the two slopes above and below it are basically the same. And below it, they're ramping up, and above it, they're slowly going back down to 0. So you'll see something like this. You'll see, so here you'll basically see it flatline, then above it will start going up. It'll keep going up, And right about here, it will reach its peak and it'll start going back down again. I'll get something like that. And of course, this would be mirrored across the whole thing because the rate is purely dependent on population and not time. So which solutions are increasing? So when is our population increasing? Well, if you look on this graph, which pretty close representation of what it will be, it's always increasing. Here it looks like it's leveled out, but it's technically still increasing ever so slightly. You just don't consider it when you have actual integers for population, because then you'd suddenly have 0.999 of something. Clearly that doesn't happen. So we do say, so what or which solutions are increasing? You're just going to be going from 0 to 100 for P, because that's all this is you're hard limited here. So increasing question mark. And that would be on the interval 0 to 100 for P. Clearly time, we would just go from 0 to infinity, but we're not considering time in this case. All right. So then which solutions are decreasing? It's kind of awkward for this. So you have to look at the direction field. So when you look at 100, you'll notice that everything levels out, and then above 100, everything is negative. So decreasing goes here. So levels out at 100, and it starts going back down. It gets steeper as you get away, because the more animals you put into a system above carrying capacity, the faster it will start going back down to their carrying capacity. Again, you can use this in a lot of different cases. It's a very real world application, at least assuming that you get into a major where you have to deal with this. So decreasing would be 100 to infinity. All right. And then again, this is related to P. So you don't need these in the answer. I'm just showing that to make sure we're talking about P and not T. All right. And then use the direction field to sketch solutions for initial populations 20, 40, 60, 80, and 120, and 140. So what you would do in this case, it's kind of hard to write this. Let's see, it has plenty of options. So what do these solutions have in common? How do they differ? So let's say, so we know that our carrying capacity, let's say, is 100. We know that we're increasing when we're between 0 and 100, and we're decreasing when we're above 100. And then we'll typically follow a logistic curve like this. But I think it varies. Let's see. Yeah, actually, so above 100, we'll be following something more like this, where it's steep all the or it gets steeper as we go up, and then it shallows out. And then here, starts shallow, and then it starts ramping up, and then it starts ramping down after reaching halfway. So we have to imagine what sketches would be like for each one. So at 20, we'll start down here. You kind of start like this and go like that. At 40, we're going to be going even faster and then ramping. Something like this. 60 and 80 are the same case, actually. So that would be 20, 40, 60, 80. And then if we were at 120, we would shoot back down, level off. And then 140, we would shoot back down and level off. So all of the end goals will be along this line here at 100. And then it all depends on kind of the rate at how fast they'll get here. So if you start above 100, it's going to decline sharply and then level off at 100. If you start below 100, it's going to either ramp up if you're below 50 and then shallow out as you go above 50. Or if you're already above 50, it's going to slowly get to 100. It's all based on rates. But for this problem, I think it's mostly just asking if they're increasing or decreasing and then whether they hit a limit. So that would be for part C. So now part D, what are the equilibrium solutions? If we go back here, we already solved the equilibrium position or solutions because that's where dp dt is equal to 0 and where the slope will be near 0. So you've probably already gotten most of this work already done by the time you get here. So D equilibrium at P equals 0 and 100. And then how are the other solutions related to these solutions? So increasing solutions move away from P equals 0, and all non-zero solutions approach P equals 100 at T, or as T approaches infinity. So basically what they're saying is if we start at 0, we stay at 0. But if we have, or increasing solutions are anywhere from 0 to 100, and then decreasing solutions would be from 100 to infinity. And then everything's going to be moving away from 0 because that's kind of an unstable equilibrium. The moment you push it in one way, it's going to keep going that way. And then anything above 100, or so everything above 0 is going to approach 100. Even if it's above 100, it's going to go back down to 100 because this is a stable equilibrium. I like to think of it like this. We have a hill. So this would be an unstable equilibrium. If we push this way, it's going to go up and then roll back down to here, possibly even go there. That's the situation. If we push it this way though, it's going to keep rolling down. So think of this as our 0 point, and this is towards 100. Once we push it one way, it's going to start going towards 100 regardless. And then down here is our 100, and it's like this. Once the ball makes it here, if we push it up, it's going to roll back down. If we push it up this way, it's going to roll back down. So think of this as unstable and stable. So we're pushing away from 0, pushing towards 100. Any questions about this? All right, if there are no questions about this, feel free to ask another question. Could be on a new homework sim, could be on anything. I feel like you guys are coming up on unstable and stable equilibrium. Maybe not yet. Maybe you already have. I think that's something you cover in this class. for it later on? Probably not. These are population growths. It's all stable. Well, there's one stable, one unstable solution. Unstable one happens 0. No questions? We got 18 minutes still.
Could you go over the 9-3 homework, number 12?
Great. Yeah. Oh. 9-3 problem 12. Might let you do this. Yes, it's always the last problem. How comfortable are you with Brian?
You can take that problem.
Okay. So we got 9.3, number 12. All right, so tank contains 9,000 liters of brine. So I always write out things as variables real quick. So I'm saying V naught, the initial volume of the tank. So 9,000 liters. And then it already starts off with 17 kilograms of dissolved salt. So what we do then is we have, so I like to just do mass. I can do Na or salt, however you want to do it. So mass of salt, actually, because we're probably only dealing with one mass, we just deal with just M. So M is equal to 17 kilograms. And then, so pure water enters the tank at 90 liters per minute. So pure water, and then I'm going to do a dV dt equals positive 90 liters per minute. All right. And then the solution is kept thoroughly mixed and drains from the tank at the same rate. So that means, we'll just call it tank solution. Or tank brine, however you want to say it. dV dt is equal to negative 90 liters per minute. So we're putting pure water in and we're losing our salt mixture at the same rate. That would be 90 liters per minute. All right. So we need to find an equation for how much salt is in the tank after T minutes. So we need to find first, what's the rate at which we're losing salt? So we're going to do a dm dt equation. So how we do this is we're going to do conversion. So we have liters and kilograms. So, and then liters per minute. So we need to find out how many kilograms per minute we're losing. So we're going to be losing, all right. So we're losing 90 liters per minute of whatever solution is currently. Its initial condition is 17. So I should be saying that this is M naught. So we have, all right. We have our mass divided by V naught. And since this is unchanging, we can keep it as V naught. It doesn't have to be a variable V. And then times, so now we have kilograms per liter. And then if we multiply by liters per minute, we get kilograms per minute, which is the same as the units that we should be getting over here. So that would be our 90 here. So it would be dV dt. So I'm going to write that first. And then keep in mind that this will be negative because we're losing salt, we're not gaining salt. So what we do is then, okay. So you get mass, because this is going to be a changing variable, over that, and then times -90. So since we have 9s in both of these terms, we can cancel that to 1. We got 1,000, or 10 over 1,000. You can cancel the 0, or cancel the 10 here, lose the 0 here, keep the negative sign, and we get dm dt is equal to, so -m over 100. All right. Oops. Then we need to find out how much salt is in the tank after t minutes. So we need to find m of t. So in order to do that, we solve this. So we need m's on both, or we need the m's on the same side, dt on the other side. So we divide by -m, or actually we're going to just divide by m. We'll keep -1 over 100 over here. So we get dm over m is equal to -dt over 100. Integrate both sides. So this is 1 over m, will become natural log of m. And then this is just constant, so it'll be -1 over 100 t. To solve for m, just e both sides, and we get m of t is equal to, also don't forget that this is a plus c out front here. So we get m of t is equal to e to the -1 over 100 t plus c. So because we have addition in the exponent, what we can do is we can relate this to e to the -1 over 100 t times e to the c. This is just a constant to a constant power, so it becomes just a constant. We get this as our end result, c e to the -1 over 100 t. And now we just need to find our initial condition. Well, we already know at t equals 0, m is equal to 17. T equals 0 turns e to the 0 to 1. So c has to equal 17. So with this, we now just solve for t is equal to, oh yeah, so how much salt is in the tank after t minutes? There's our solution. Oops. So m of t is equal to 17e to the -100, or 1 over 100 t. I'll change for each of you because, again, different solutions, but this is the base work on how to do it. So then how much salt is in the tank after 30 minutes? You just plug it in here, get your answer. I don't really have a way of calculating this on me right now because I only have my phone as a calculator, and it's gonna have a hard time typing that. So any other questions? We are 10 minutes left. So I have enough for probably one more problem. I should add one short problem. If nobody has any problems, you're free to go. You're always free to go. We'll try to make the recording available. Don't exactly know how that's going yet. I myself can't make the recordings because currently my recordings will go immediately to Canvas page, and I don't want it going there. No. If there are no questions, I hope you all have a good night. Enjoy the rest of your day, though I don't know how many of you. Well, actually, we're all college students. We stay up late.
Thanks.
No problem. All right. I think we can stop recording.